Who did not take the class last semester, or is it on the class last semester? Okay. You're just auditing. Okay. So everyone more or less knows what the deal is. There's not too much different from the way the course is going to be run this semester from last semester. My name is still Alex. Scott's name is still Scott. He's still the TA. We have slightly different office hours, which are posted here. The classroom is this classroom, which you figured out. Remarkably enough, nobody went to the one that was listed on Minerva. Let's see. Yeah, as with last semester, if you're not registered for the course, but you are attending the lectures, send me an email so I can add you to the email list, because like if I have to cancel the course or reschedule something, that way you can be notified. Grading, it's just going to be problem sets this semester, no final or anything like that. Although the final was fun. Did you guys enjoy the final? Was it exciting? It was pretty good. It was pretty fun, right? It was fun to grade. So let's see. Do we need to go over this? I mean, it's all the same stuff I said last semester. Problem sets, you have to turn in your own work as opposed to someone else's work. If you're going to be late, you'll be penalized unless you get an extension from me or Scott the day before or before it's due. The textbook, I'm going to keep using Schwartz as a textbook, I think, because it's actually quite good for the stuff later on in the semester when we get to the standard model. So I think we're going to stick with it. But I am going to sort of lean a little bit more heavily on Srednicki as an alternate text. I think it's very good. It's pretty different from Schwartz. And it's also available online for free. So like if you go to the course webpage, we'll have a link to it. So at least the draft version of Srednicki's book is sort of publicly available for free. And it's practically the same as the published version, except it has a few more exciting typos for you to check out. Just a word about supplementary reading you might want to take a look at. A lot of the sort of standard quantum field theory books that I like Ryder, are great, but don't have quite as much of the more advanced stuff that we're going to be studying this semester. So I think Dave Tong's lecture notes are great, Ryder is great, Z is great, but you may find that after the first few weeks, month of this course, they're not actually covering what you need them to cover. Peskin and Schroeder is great, but there are a couple problems with the way that he presents renormalization, but aside from that, I think it's really great, so that's one I really recommend. Tom Banks's book on renormalization is really great and kind of quite different, so you should take a look at it if you want a good resource on renormalization. It's quite advanced, so you should be prepared for that, but it's great. And then the other thing is that I am going to try and do a little bit more of applications of condensed matter physics this semester. Zinn Justin's book is kind of the classic. It's also like a telephone book. I mean, it's like 1,500 pages long or something. So it's not the sort of thing you're just going to want to like browse through on an idle Sunday afternoon, but it is really good. So you should consider taking a look at that. This course is going to be more or less a continuation of last semester, so the administrative details are really not any different. I did give a brief syllabus at the end of sort of an outline of what we're going to study. Note that the word renormalization is used 1, 2, 3, 4, 5 times in the first 2 lines of the course outline. That's really kind of the heart of what we're going to be studying this semester. So from my point of view, there are 2 important things that we're going to study this semester. First, we're going to study renormalization, and then we're going to study non-abelian gauge theory, that is to say Yang-Mills theory. Renormalization is kind of the core observation and tool that we use to understand quantum field theory, not just in particle physics, but also in applications to condensed matter physics, to cosmology, and so forth. So we'll be starting with a kind of, I'll say, old-fashioned approach to renormalization, a kind of sort of standard textbook approach to renormalization as you might have learned it in a class 20 years ago. So in this case, we'll be doing things like doing a detailed study of the renormalization of scalar field theories and of quantum electrodynamics. And we'll be, along the way, sort of using what we learn about renormalization to understand how perturbative corrections are computed sort of precisely in quantum field theory using Feynman diagrams, before moving on to a kind of more general approach to renormalization using what's known as Wilsonian renormalization and the renormalization group. And this is really, I think, where quantum field theory shines. It's where you can kind of understand quantum field theory as a general tool for studying the dynamics of all sorts of different systems. So effective field theory is kind of the buzzword here. It's the strategy that we use to, if I hand you a physical system, you identify the symmetries of that system, you make a guess for what the basic dynamical degrees of freedom are for that system, and then effective field theory gives you a recipe for studying the dynamics of that system systematically at low energies. So, for example, effective field theory is of course used in particle physics all the time. So the Standard Model is believed to be an effective field theory that is an approximation to some more fundamental theory. But if you study nuclear physics, there's effective theories of nuclear physics. But in addition, in condensed matter physics, when we talk about the quantum field theory descriptions of various condensed matter systems, we're always talking about effective field theory. And even in the last several years, effective field theory has been used to study cosmologies. When we study the large-scale structure of the universe, there's an effective field theory that describes that. It's an effective field theory involving broken symmetries, just like the effective field theories that describe nuclear physics. So it's a very, very powerful common language that we can use to study physics in all sorts of different regimes. And that's kind of, I think, the heart of this second semester of field theory. So kind of the first, I would say, half of this course is going to be spent this semester on renormalization. I'll try and be generous about throwing in applications to things aside from particle physics. I'm going to try and talk a little bit about the theory of critical exponents and universality classes in condensed matter physics. We'll see how that goes. To some extent, that depends on how quickly I can get through some of the earlier material. And then in the second half of this semester, we're really going to be diving into the quantum field theories that are relevant for the Standard Model of particle physics. So we'll talk about Yang-Mills theory, otherwise known as non-abelian gauge theory. This is the generalization of electromagnetism to describe the nuclear forces, the weak nuclear force, and the strong nuclear force. We'll talk about quantum chromodynamics, which is the theory of the strong nuclear force describing the interactions of quarks and gluons, before moving on to the electroweak force. The electroweak force is interesting because it will be the first example that we'll encounter this semester of a theory with broken symmetries, with spontaneously broken symmetries. So to understand that, we'll need to understand the Higgs mechanism, which of course is very exciting because we just observed the Higgs boson, which is the particle associated with the Higgs mechanism. And we'll probably also talk about some other examples of spontaneously broken symmetry. So for example, superconductivity is a theory of spontaneously broken symmetry in the BCS model. And then finally, at the end, we'll sum it all up by describing the Standard Model. We'll see how far we get. I mean, one can teach a whole course on the Standard Model, and there is a whole course on the Standard Model taught here every other year. So, of course, we won't get into a huge amount of detail, but we will talk a bit about the Standard Model, some of its features, and we'll see how far we get there. Are there any questions about the organization of this course, about structure, about what we will or will not cover? Any thoughts? Yes?
About the type of the course,
Mhm.
isn't it something have changed? Because string theory, it's at the same time. There's
This is the 500 level string theory class?
Yeah.
Yeah. I mean, it's fine with me. It's the problem, so if we wanted to change the time of the course, that I guess is fine with me, but it's a matter of seeing that everyone's available. Who's teaching? Is Johannes teaching?
Yeah.
How many people would be taking that course if it were, I mean, just two, okay, more. Yeah, I mean, it's a pretty basic, like if you actually want to learn string theory, I guess there's no harm in taking that course, but it is pretty elementary. I mean, that course is kind of geared for people who don't know quantum field theory. If you know quantum field theory, you should do a real string theory course. Now, of course, we don't have a real string theory course this semester.
Despite what Minerva tells you.
Despite what Minerva says. Yeah, Minerva is like haunted. because like it's always showing weird classes that don't actually exist, and some classes do exist that don't show up on Minerva. So, you know, it's very exciting. Yeah, I mean, I don't discourage anyone from taking that class, but it's not like the most awesome introduction to string theory because it's pretty elementary. Although maybe Johannes is, do you know what textbook he's using? Yeah, if he's using Zwieback, it's pretty elementary. I mean, I would recommend, you know, set aside a weekend and read through Zwieback, and you'll be fine. But we could talk about, I mean, we could change the time of the course. There's only like 10 people, you know, there's not that many people in this course. So I'd be happy to change it if that's more, if that would make people's life easier. I mean, what time is Johannes' course? It's exactly this.
Yeah.
I mean, let me think. We could go earlier on Tuesday, Thursday, 1 to 2:30. Is there anyone who would object? You would, because you guys have course. Okay, you three. I mean, I don't want to go later because it's a little. It was a little, like 4 to 5:30 was a little late in the day, and it's kind of hard. You know, I'd rather not go later. I mean, we could go like Monday, Wednesday. We could go to mornings. How do you guys like the mornings? You like the mornings? Not everyone likes the mornings. I mean, if we had it like, what, like at 11? 11? Tuesdays, Thursdays? There's the GR. How many of you are in GR? A couple of you. How many of you are in GR? A couple of you are probably in GR. When is GR? 10:30 to 12. Okay. I think going 9 is difficult for me. You know, 9 is difficult for me. I can do it, but like, you would have to pay me more. I would have to be paid more than I'm being paid now to teach a class. Yeah, I would have to be paid more than I'm. What's that?
Mornings, Monday, Wednesday, like 11.
Mornings
are already.
What? What about Wednesday?
Sorry, we normally have
Monday,
seminars
Wednesday.
going on at
Yeah.
12 on Monday.
Yeah, I mean, we could do Monday, Wednesdays morning, 10-ish.
Number
Easier for spring theory to change this time if there's only 4 or 5.
Are there only 4 or 5 people registered?
I made Mr. Johannes and he told me that cannot change.
Yeah.
He
Okay.
can't
Graduates.
Can't.
officially change.
You can't
how it's
officially.
listed,
You
but
can't
he can
officially.
move it.
You can't officially. You can never officially do anything. Basically, you can all like. I can't officially change the location of this room, but I can book this room and tell people to come here, and that's fine. So it's like I can't officially change the time of the course. I could unofficially do it. I mean, what about Monday, Wednesday mornings? Was that impossible for people?
Number theory is at 10. Number theory is at 10.
Okay. And then we have 12 to 1. Like Monday, Wednesday afternoons. You guys are busy. This is the problem. This is Monday, Wednesday afternoon. You said you were busy. Or no? Does anyone know? Are you? Is that a yes that you're busy? Okay. All afternoon. More or less. Yeah. See, this is the problem when you try and reschedule classes. It never actually works. Ask Johannes again, because he's a nice guy. I mean, usually. Yeah. Go ask him again. And yeah, unless anyone else has any bright ideas. What's that? Wednesday, Friday? Monday, Friday? What's your problem? Your problem is Wednesdays or Mondays? Or Monday,
Wednesday, Friday.
Yeah, Monday, Wednesday, Friday. I'm running out of days. We could also
Saturday, Sundays.
What's that?
Saturday, Sunday.
Yeah. I mean, yeah.
I'll do 11:30. Could we do 11:30
On
Tuesday?
we could do 11:30 to 1 on Tuesday, Thursday. I'm trying to think. Do we have? Because usually lunch. There's a lot of seminars at lunchtime. So I'm
We
hesitant.
don't usually have them on Tuesdays and Thursdays.
So you guys want to do 11:30 to 1 on Tuesday, Thursday?
I get lunch.
You can't make it. Okay. Yeah. I don't know. I think that it's like, this is the thing. If you get 15 people in a room, like nobody's ever going to be able to make it at any given time. Okay. Okay. Oh. Sorry. You're being pulled all over the place here. Is that okay? Yeah. Okay. Well, I guess we're just going to have the class when it's scheduled. And that, I mean, we could do 4 to 5:30. It's sort of not an ideal time at the end of the day. How many people, did people mind having it We could do 4 to 5:30 if we need to. It's not ideal for me, but we can do it. Do people want to do that? How many people would rather have it from 2:30 to 4 versus 4 to 5:30? Raise your hand for 2:30 to 4. Okay, and you're okay. So you're the one asking us to reschedule it. So if you're voting for, so if it's not worth.
Ask Johannes to move his class to just.
Tell Tell Johannes that I want him to move the class. Okay, and then maybe
You can
he'll
tell
probably.
Johannes that you want him to move it.
But it's so much more fun if I communicate through the medium of graduate students. It's very low bit rate, but it's a more fun way of communicating. Okay, good. Okay, so let's just start out with some physics. So.
Well, you're not giving them a final this year.
Yeah, no finals. I mean, you're all adults. Like, it's time to leave behind childish things. At some point you grow up, you leave behind your teddy bears and your stuffed animals. And, well, you can keep your teddy bears and your stuffed animals, but finals I think you can leave behind. So no finals. I mean, unless someone wants a final. Do you want a final? No? Yeah, you want a final? You enjoyed it? You can have a final.
I did.
Okay.
My suggestion would be a
We-
smaller final in the sense worth less. I don't know, 20%. Everyone's gonna hate me, so.
Do you want how many? Let's take a vote. Who wants a final? Raise your hand if you want a final. What if we had? What if we had a final problem set that's worth as much as a problem set, but is called a final? Would you like? Would you like that? Sometimes people do this. Actually, they have a quote unquote final problem set. Is that what you? Yeah. Yeah.
Change the title.
Yeah. Do you want to? We can do that. Or you could have a final. I could give you a final. And then yeah. Yeah. Do you want to? How many people? Raise your hand if you'd like a final. It's okay. You can raise your hand. It's fine. It's fine. How many people would rather have a final than just problem sets? Okay. Okay. We could just do problem sets. Let's just do problem sets then. Okay. I'll call the last one a final. But yeah, I'll call it the final. That way everyone will be happy. Okay. Good. So. Last semester, we developed a systematic way of understanding perturbation theory in quantum field theory using the Feynman diagram expansion. But we really only focused on the leading terms in the Feynman diagram expansion of, say, scattering amplitudes or correlation functions in quantum field theory. And we really did very little to discuss the computation of perturbative corrections involving loops in Feynman diagrams. And one reason is that, of course, in a perturbative expansion, the subleading perturbative corrections are small. So loop corrections in quantum field theory will be relatively small. But we also saw that these loop corrections in Feynman diagrams, in the Feynman diagram expansion, often are naively divergent. And we saw this in a couple different contexts, and one of which I'll remind you of in just a few minutes. But the important point that one always has to keep in mind when thinking about these divergences in quantum field theory is that these divergences are always unphysical. Well, I shouldn't say always unphysical. These divergences, unless they have a physical meaning, are unphysical. I suppose that's a bit of a tautology, but that doesn't mean it's not true. The ultraviolet divergences, let us say the short distance divergences that arise in quantum field theory, are always unphysical. And these divergences in the computation of loops in quantum field theory arise when we compute the wrong quantity. That is to say, when we compute unphysical quantities. And what we always want to keep in mind when we encounter a divergence in quantum field theory is that physical quantities, that is to say physical observables in quantum field theory, are finite. But it's very easy to get confused and to compute something that you think is physical but is secretly not observable and hence has some sort of divergence. Okay? And so what I'd like to do is I would like to start by recalling an example that we discussed on the last day of class in December. So I don't remember exactly how much detail I discussed this example in, so I'm just going to remind you of this example, just so that we have, just because it's a great example, to understand the origin of some of these divergences as well as their cure, before we try and implement more systematically the procedure by which infinities are removed from the computation of physical quantities in quantum field theory. Okay. So the example that I want to consider is massless phi to the 4 theory. Okay. So this is a theory of a scalar field with a kinetic term where I've set the mass equal to 0, and I wish to consider the scattering of 2 particles into 2 other particles. So the amplitude for that scattering I'll call m, and at leading order, that's just given by this tree level diagram, which is finite, and it's just given by lambda, okay, the value of the coupling constant appearing in the Lagrangian. However, at next order in perturbation theory, there start to be loop corrections. So for example, here's one loop correction. Okay. You can see that it's proportional to lambda squared because it has 2 interaction vertices, and it also has 1 loop integral. Remember that the way that we proceed when we compute Feynman diagrams is that we enforce momentum conservation at each one of the vertices in a Feynman diagram, and then we integrate over all of the undetermined momenta. So for example, if I let P1 plus P2 equal to P, then there'll be 1 undetermined momentum, so this would be that I've called K here, and one could always do a change of variables to let, K plus 12 or K plus P or K minus P or something like that be the undetermined momentum. But the answer at the end of the day will not affect whether or not you do a change of variables like that. So here, for example, I've called the lower leg of this loop in the Feynman diagram the undetermined momentum K. I could have called it the upper one if I wanted to. That would just be some change of variables in the integral over the undetermined momentum at the end of the day, and it wouldn't actually affect the final answer. Okay. Now, actually, this is not the only contribution to this 2-to-2 scattering amplitude at this order in perturbation theory. This is the S-channel contribution. There are also T and U channels. And just for the purposes of illustration for this example, I'm just going to consider the S-channel for today. Okay. If you wanted to actually do the computation correctly, then you would need to consider the other channels as well. But let's just talk about the S-channel, because really I'm not trying to write down a precise answer, but more to make a point. So do you remember this? I did this the last class of last semester, right? Okay. So I'm going to just do it in a little bit more detail now, just to highlight some features that we're going to be using later on in this class and for the next couple of weeks. Okay. So what is the value, this contribution to the scattering amplitude? Well, you have the coupling constant squared, you have a symmetry factor of 2, and then you have the integral over this undetermined momentum. And then you have 2 propagators, a 1 over k squared propagator and a 1 over p minus k squared propagator. And the important point is that if you stare at this integral for a second, it's an integral, and you think about how it behaves when k is very large, then you see that it's an integral d4k, but it's got 4 powers of k in the denominator. So if k is very large compared to p, then this looks like an integral d4k over k to the 4th, which is logarithmically divergent. So the question then is how we should deal with this log divergence. So the simplest thing you could imagine doing is just cutting off this integral at very large values of the absolute value of k. And then you could go ahead and perform this integral where we integrate d4k, not over all values, but where we cut it off at some very large value of k, let's say lambda. So if we cut off the integral, probably misspelled cutoff there, at values of k which are less than some scale lambda, then you know that this should be, you should get a divergence in this integral which looks like the log of lambda. So in particular, just by Lorentz invariance, you know, so lambda is a dimensionful quantity. It has dimensions of energy. And by Lorentz invariance, you know that that integral right there has to be a function of p squared, that is to say s. So s is the Mandelstam variable, p squared. So you know just by the dimensionful scaling of this integral that it's log divergent, and the fact that it has to depend on s, that the leading term in this, in lambda, has to go like log s over lambda squared. Here, I put in a lambda squared here because s has dimensions of energy squared. And this is really by Lorentz invariance. And just the scaling properties of this integral as you rescale k. Dimensional analysis, essentially. So later on, probably next class, we're going to develop a whole set of technology for computing integrals like this. They're really not that hard to compute. In fact, when we compute integrals like this in this course, we're generally not going to be introducing a hard cutoff. That is to say, cutting off the value of the k integral at some finite value of lambda. We'll be introducing some more sophisticated kinds of ways of regularizing or cutting off these integrals. But for now, let's just talk about this hard cutoff method, where we just cut off the integral at some absolute value of lambda. And then if you do that, it's a sort of straightforward calculation to go ahead and compute this integral. Because we're going to be spending a lot of time later on this semester doing this calculation, I'm not going to bother computing that cutoff integral for you right now. I'll just tell you the answer. So it goes like log s over lambda squared, where lambda is the cutoff, times the coupling constant lambda squared, along with some numerical coefficient. Okay, so that means that if you go ahead and compute the 2 to 2 scattering amplitude, okay, there's no factor of I there, you get the leading contribution, which was lambda, and the subleading contribution coming from the one loop correction, which is small in the sense that it's order lambda squared rather than lambda, but it also naively has a logarithmic divergence. So it's a little confusing because ostensibly it's second order in perturbation theory because that coupling constant little lambda is small, but naively you might think it's divergent because it has the log of capital lambda here, and capital lambda is some very small number. It's the place where we cut off the integral. So as you took capital lambda to 0, this second term would appear to be logarithmically divergent. So this naively appears to be a disaster for quantum field theory because you have an infinity, you don't know what to do with it. Well, you don't know yet what to do with it. And so it appears that quantum field theory is really failing. But here is where we really have to remember that physical quantities are finite and that we really need to phrase the answer here in terms of physically observable quantities. So I've written the answer for the 2 to 2 scattering amplitude m here in terms of the coupling constant lambda, which typically goes by the name of a Baire coupling constant. And lambda is a parameter that appears in the Lagrangian, but it is not something that is directly observable. You don't observe a Lagrangian. What you observe is things like scattering amplitudes or correlation functions. The 4-point function, or 2 to 2 scattering matrix element, is something that is observable. So the question then is, how do we rephrase our answer for the scattering amplitude m in terms of something that's physically observable? And the answer really arises if you think carefully about what it is you mean by this coupling constant lambda. Okay. Lambda is supposed to measure the strength of the interactions between two of these phi particles. And so a perfectly reasonable definition for the coupling constant of the theory is simply that it's equal to minus the 2 to 2 scattering matrix element at some particular value of energy that I'll call S naught here. So really what we want to do is we want to think about the physically observable coupling constant, which measures the strength of the interactions in the theory, as being defined as the 2 to 2 scattering amplitude at some particular value of S that I've called S naught. So indeed, you could see that if you just looked at tree level, then this scattering amplitude m is just equal to minus lambda, the coupling constant in the Lagrangian. And so that at tree level, this is a perfectly consistent definition. This is the correct definition. And so lambda sub r is equal to lambda at tree level. But then once you start including loop corrections, you have to include this second term here that involves the logarithmically divergent term. And so lambda sub r is often referred to as a renormalized coupling, hence the subscript r, or sometimes it's just referred to as the physical coupling. So then we could take this formula for lambda of r, the renormalized coupling, in terms of Baire coupling lambda, and you could then go ahead and solve for lambda in terms of lambda sub r. That's just some trivial algebraic manipulations. So I've just written down the answer here. All I've done is taken this formula here for lambda sub r in terms of lambda, and I've inverted it, working only to quadratic order in the coupling constant lambda, which is assumed to be small. And then you could go ahead and plug that back into our formula for m up above. So we could go ahead and plug that into our formula for m. And what you're left with, so let me write this out a little bit more carefully, is an expression for the 2 to 2 scattering amplitude written in terms of the physical coupling lambda sub r. So let's just take a second to stare at that expression here. So you can see what we've done is we've written the 2 to 2 scattering amplitude m at any value of the center of mass energy s in terms of its value at a particular fiducial value of the center of mass energy s naught. Okay? And so, of course, when s is equal to s naught, that subleading term vanishes, and the scattering amplitude is just lambda. And so what really the scalar field theory is doing for us is it's allowing us to relate the 2 to 2 scattering the values of the 2 to 2 scattering amplitude at different values of the energy. Okay? Because, you know, the original coupling lambda and the Lagrangian is not something you ever observe. All you ever observe are scattering amplitudes. And so all the quantum field theory can do for us is relate different values of those scattering amplitudes to one another. Okay? And so once you think about quantum field theory in that sense, not as computing scattering amplitudes in terms of some constants appearing in the Lagrangian, but rather describing a set of relationships between different scattering amplitudes, then everything is going to be nice and physically finite. Okay? And you can see, you could think about this 2 to 2 scattering amplitude really as defining a coupling constant lambda that is a function of the energy scale s. And so you see that what's happening here in this expression is that the value of that coupling constant is depending logarithmically on s. Okay? So as you probe the theory at different energy scales, the theory might appear to be either more weakly or more strongly coupled. Okay? And that's something that is going to come back again and again in this course. Okay? That's a sort of universal feature of quantum field theory. The fact that it has a logarithmic dependence on energy scale as opposed to, say, a power law dependence on energy scale is a special feature of phi to the 4th theory. It'll be shared by some other theories that we study, but not all theories. In other theories, you might have a polynomial dependence on energy rather than logarithmic. Okay. So the essential point is that in quantum field theory, we really only relate different observables to one another. And if we do so, you know, if you write down expressions for scattering amplitudes relating one observable in terms of another observable, we never encounter divergences. We never have what are known as ultraviolet divergences. That is to say, short distance divergences that would appear when that cutoff lambda is taken to 0. Question?
Do you know if there is any...
Sorry, infinity. Yeah.
Do you know if there is any other elementary example that you can see this distinction between the physical coupling constant and the...
Yes, absolutely. I mean, this is going to happen again and again and again.
I mean,
Yeah.
not in field theory. So, I mean, I have in mind something like the coupling constant of the harmonic oscillator.
Well, I mean, you know, this sort of happens all of the time. So, you know, an example would be, say, the value of the electric charge.
Yeah.
Okay, you're not happy.
Classical mechanics from classical mechanics.
I mean,
for example, if we take the
let
Lagrangian
me-
harmonic function.
yeah, okay. I mean, you did an example of this in one of your problem sets last semester where you studied the Casimir energy. So you take a pair of parallel plate capacitors, and then strictly speaking, there's a divergence. If you calculate the energy in the quantized electromagnetic field between the two parallel plates, then you found a divergence. But energies are not observable, and when you phrased it in terms of observable quantities like forces, then you found a finite answer. So that's a pretty elementary example. Yeah.
But I'm referring only to coupling constants. I don't know if there's...
Yeah. I mean,
For example, if we take the Lagrangian the harmonic oscillator from classical mechanics,
yeah.
the coupling K, it's both physical and there, but...
Right. I mean,
It's kind of like having a generalization of a mass square field.
Yeah,
That's the closest thing we can get.
yeah. I mean, yeah. I'm not quite
But
sure.
we don't, okay.
How about this? We're going to find examples of this again and again over the next few weeks. So,
But what something that happens only if it's in a field theory, with coupling constants.
Well, I mean, it's a field theory effect.
Because we have local.
That's right. That's right. I mean, we could probably come up with analogies in classical mechanics. But yeah, but yeah, I don't know how strong the analogy would be. I mean, there are very often cases, you know, in classical physics where you can compute things that are naively infinite but are not observable, like the self-energy of an electron in electromagnetism is infinite, but it's not actually observable. So that's the sort of thing, you know, what you really observe are energy differences. So that's the sort of thing that can happen in classical physics as well. Okay, and so if we wanted to, we could then proceed to go ahead and continue to study quantum field theory in this vein. So in particular, we could proceed to study interactions carefully in quantum field theory by introducing physical, that is to say, renormalized couplings, and then rewriting everything in terms of these renormalized couplings. But in practice, this tends to be a bit cumbersome. And in practice, what we're going to use is a somewhat simpler algorithm using what are known as counterterms. So counterterms, of course, are something that we encountered in a couple different contexts last semester. But I wanted to spend a few minutes just to introduce them a little bit more systematically. So in particular, let's consider again the case of massless phi to the 4 theory. So you could imagine studying the theory with a coupling constant lambda that's now equal to its renormalized value, its physical value, where it's defined to be equal to the 2-to-2 scattering amplitude at some particular value of the energy. And then we could introduce another coupling that I'll call delta sub lambda, which is, I'm going to include just as another coupling constant in the theory. This is known as a counterterm. And the sole purpose of this term delta lambda is just to, order by order in perturbation theory, enforce our definition of lambda sub r as the value of the 2-to-2 scattering amplitude at S naught. Okay. And so in particular, this delta sub lambda, you know, if you write it in terms of the cutoff scale capital lambda, is going to be formally divergent, but we will treat it as being of order lambda squared. Okay. So in particular, we could go ahead and compute, say, this 2-to-2 scattering amplitude. And then if you work at order lambda squared, then at tree level, you'll just get the tree level coupling, so that's lambda r minus plus delta. And then you'll get this quadratic term, but we're going to treat delta as of order lambda squared, so that if we only work to order lambda squared, then these are the only two contributions to that scattering amplitude. And then we fix the renormalization constant, delta lambda, by setting lambda renormalized to be the value of the scattering amplitude at energy S naught. So that means that at second order in the coupling, delta lambda has to be equal to minus lambda r squared over 32 pi squared log s naught over lambda squared, just so that when you evaluate the scattering amplitude at energy s naught, you get minus lambda sub r. And then plugging that back into our answer, we get exactly what we found earlier for the subleading correction at order lambda squared to the 2 to 2 scattering amplitude. So the introduction of this counter term is just a sort of polite fiction that allows us to slightly more efficiently keep track of the various divergences that appear in quantum field theory when we write things in terms of unphysical quantities, like parameters in the Lagrangian, as opposed to physical quantities, such as normalized couplings or physical couplings. And the general strategy that we use when considering these counterterms is that for each possible coupling constant in the Lagrangian, we introduce a counterterm whose only role is to, quote unquote, absorb the divergence that appears in the loop expansion of quantum field theory. And we fix the counterterm order by order in perturbation theory to enforce a physical condition. Such as the definition of a physical coupling. So is this strategy more or less clear? One of the things that we're going to do in the next couple of lectures is understand a somewhat more systematic strategy where we determine exactly what counterterms we need to introduce in a quantum field theory, how many counterterms we need to introduce, and how this affects the general ability of a given quantum field theory to make useful predictions. But hopefully at least the general strategy is clear and how it's implemented in this specific case is clear. Any questions on this? No questions?
I'm curious about the mixing of loop orders.
Yes. Yes.
I think it's
Right.
when you're looking at anomalies, you get a certain loop order cancels before it.
That's correct. That's right. I mean, so this, yeah, okay.
I'm just wondering if it happens in, so that's an anomaly calculation, so I'm wondering if it happens in more conventional examples.
Well, there's a sense in what we're doing here is we're balancing different orders in a perturbation series against each other, in the sense that delta lambda is a term that's appearing in the Lagrangian, so you might naively think it's a tree-level quantity, but we're setting it to be of order lambda squared, so second order in the coupling constant, the real coupling constant. And so what we're doing is we're taking this tree-level term and we're balancing it against this quadratic term. So I understand so that's maybe not quite what you're thinking of,
I guess
but
what you were saying is feels sort of a semantic difference.
yeah. I mean, certainly in the case of anomalies, there are cases where there are tree-level effects that need to be balanced against one-loop effects and things like that. Those are really, I guess I would say, what we're doing here is much stupider, okay? Because what we're doing here is really just introducing delta as a bookkeeping device to keep track of renormalized versus bare coupling constants in the Lagrangian. Whereas when we talk about anomalies, it is literally, that's like a physical effect. where we really have. So I would sort of draw a contrast there. We will get to anomalies at the end of the semester, though, and we will return to that, presumably. Yeah. Other questions? Good question. Yes.
How do you decide that delta lambda is order of lambda r squared?
Let's put it this. Yeah.
Besides the fact that it works out if we say that.
Well, the answer is that it works out if we say that. Maybe a slightly better answer is that remember that at we want to define our coupling constant lambda sub r to be the 2-to-2 scattering amplitude at some value of the energy. And that only works if delta lambda is of order lambda squared. So, for example, there may well be, let's put it this way, there are going to be there could be other sorts of theories where loop diagrams only appear at order lambda cubed, okay, lambda to the fourth or something like that. In that case, you could introduce a counter term and say, well, it's only lambda squared, but then if you start trying to enforce these physical conditions, you'll see that actually the coefficient that's of order lambda squared is 0, and then it would be some higher order. Okay. I don't want to set it to be some lower order, because then it would be competing against the classical effect. I want it to be a quantum effect, so it has to be at least quadratic, but there's no rule that says it has to be non-zero at quadratic order.
Okay,
If that's
so
what
when you
you
say
mean.
it's order lambda squared, you don't mean like if lambda is something dimensionful, then delta sub lambda will have those dimensions squared.
That's correct, yeah.
Okay.
So one of that's actually an excellent point. The coupling constant lambda that I've introduced here is dimensionless. Okay, that's why I started out by talking about phi to the fourth theory. When we talk about dimensionful couplings, we need to be a little bit more careful about the scales that we introduce. Yeah. What I mean when I say it's of order lambda squared, I mean I treat it as one order higher in the perturbation expansion when I do the Feynman diagram expansion. So that, for example, I don't need to, in this term, include a delta squared term. Now, if I want to, now what I really want to do, so here I've only done this, calculated this counter term at leading order. If I wanted to, if I was particularly powerful, I could try and compute 2-to-2 scattering at higher order, at order lambda to the fourth, say. And then I would need to go ahead and compute this counter term at higher order, okay? And so I really need to enforce this condition, physical condition, the definition of the normalized coupling, order by order in perturbation theory. Okay? And so, for example, there would be, contributions to delta lambda that are of order lambda to the fourth that would be needed to cancel other terms that appear in this scattering amplitude m at order lambda to the fourth. Hopefully that's more or less clear. Good. Other questions? And, okay. So the question then, so the general strategy, too many R's in that word, the general strategy then is that we introduce these counter terms in order to enforce these physical conditions. And the question then is precisely what sort of physical conditions are we trying to enforce? Okay. In the present case, I introduced one physical condition, namely that the value of the coupling should be defined to be the scattering amplitude at some particular value of the energy. But more generally, you could ask, what exactly is it that I mean by these physical conditions? And in fact, we have already introduced these physical conditions when we defined interacting quantum field theory. So let me just remind you of something that we touched on last semester. So remember that in free quantum field theory, so let's just take, for definiteness, a massive scalar field. Then in free quantum field theory, the Hilbert space is perfectly easy to study. It's a Fock space with no particle, one particle, two particle states, and so forth. The observables are this field phi, and the crucial properties that define the no particle state, which is the vacuum state, and the one particle state, which we denoted k, that defines a state with momentum k, are given by these two formulas. So the vacuum state, 0, is essentially defined so that the one-point function of the field in the vacuum vanishes. And the one-particle state, k, is defined so that the operator phi creates a one-particle state with momentum k. And what do we mean by that? We mean that if you take phi of x and you act on the vacuum state, you take the overlap with a one-particle state k, then you get the wave function e to the ikx describing a particle with momentum k in position space. So, and here, k is on shell, so it obeys the equation of motion that k squared is equal to m squared. Okay. And so when the point is that when we study an interacting quantum field theory, we can't really describe the Hilbert space in terms of a simple Fock space, but we still wish to impose these two conditions, which essentially define the no particle and the one particle states. Okay. So, in particular, what we argued is that if you add to this free Lagrangian here some interaction terms of order phi cubed, phi to the fourth, or something like that, then we no longer know exactly what a particle means in terms of the Fock space operators, the raising and lowering operators. But we can always preserve these two conditions here by shifting or rescaling our field variable phi. So, in particular, if you added some interaction term, and then you discovered that in terms of your field variable phi, there was a one-point function in the vacuum state, you would just shift your field variable to some new value of phi prime, which is phi plus a constant, such that the one-point function of this new variable phi prime is equal to 0. And likewise, if you found that, say, this overlap with the one-particle state was not e to the ikx, but 12 times e to the ikx, then you would just rescale phi by a factor of 12 in order to remove that. So what I want to do is try and consider that process of shifting and rescaling the field phi a little bit more systematically. Okay. So explicitly, let's just consider phi cubed theory. Just because it's really the simplest case, all of the calculations are going to be rather simple. So in this case, the Lagrangian, well, let's start with the free Lagrangian. So we have an d phi squared term and an m squared phi squared term. And then let's write a coupling term. And what we wish to do is allow ourselves to rescale or shift the value of the field phi in order to enforce these conditions. So what does that mean? That means that really, when we study the interaction theory, the interacting theory, we should put some new constant there, z, which is known as the wave function renormalization constant. And we could put a new constant there, Z sub m, which will describe the renormalization of that coupling constant m. So that's the mass renormalization constant. If we allow ourselves to shift the field in order to remove the one-point function, then we should add another coupling term, y times phi. So this is to remove the one-point function. And as we saw in the case of the phi to the 4 theory, we should allow a counter term of order phi cubed. So in order to set the physical value of the coupling, so we can introduce a new constant there that I'll call z sub g, which is the coupling constant or normalization. So we now are considering a theory with 4 undetermined constants. The wave function renormalization, the mass renormalization, the tadpole or one-point function renormalization, and the coupling constant renormalization. And these 4 constants are fixed by 4 physical conditions. In particular, Z phi is fixed by the normalization of the one-particle states. So the fact that this goes like e to the I kx is just a consequence of translation invariance, but the overall constant out front, the fact that it's 1 times e to the I kx is not, and so what we need to do is rescale order by order in perturbation theory, or adjust the value of z sub phi order by order in perturbation theory to enforce this condition. The coupling constant y is fixed by the condition that the one-point function in the vacuum is equal to 0. So again, by translation invariance, the one-point function in the vacuum has to be a constant, but that constant is not necessarily equal to 0, and so you have a one constant's worth of, so you have one equation that you need to enforce on this constant lambda, so this constant y, to set this one-point function equal to 0. Similarly, z sub g is fixed by the statement that g should be equal to the physical value of the coupling, that is, say, the physical, say, 3-point function at some fiducial value of the energy, just as we were considering for the 4-point function earlier. And finally, the mass renormalization, z sub m, is just fixed by the condition that the mass of a one-particle state should be m squared. Or I should say the mass squared of a one-particle state should be m squared. The m appearing in the Lagrangian does not necessarily have anything to do with the physical masses of the states in the theory. So of course, as we saw in the free theory, the parameter m appearing in the Lagrangian is the physical mass. But once you start considering perturbative corrections, that's no longer going to be the case. And we'll see that explicitly. So what we have here are 4 conditions on these 4 unknowns. And these conditions should be enforced order by order in perturbation theory in the coupling constant g of the theory. So for example, at tree level, order g to the 0, we just have the sort of trivial case where there's no wave function or mass renormalization. The one-point functions are 0, and the coupling constant g is just the 3-point function evaluated at whatever scale you want it to be. So there's no renormalization of the coupling constant. But at higher order, in G, these renormalization constants are non-zero and may contain loop divergences. And so they need to be fixed order by order in perturbation theory. In the coupling constant G. And in fact, we already saw this earlier in the class when we were considering tadpole diagrams in quantum field theory. We also saw this when we considered the Casimir effect in one of the problems on the problem set. So, for example, Y is fixed by the condition that there are no tadpoles, by the vanishing of the one-point function. So, in particular, the term y phi in the Lagrangian means that if you were considering the perturbation expansion in terms of Feynman diagrams, including this new coupling y phi, then there would be some new vertex, interaction vertex in your Feynman diagram expansion, where you just had one insertion of y with a phi particle coming off of that. And this counter term is fixed by the condition that the one-point function, so which if we wanted to compute it at first order in the coupling constant G would look like that, is equal to 0. So typically when we talk about these counter terms and we represent them, so these are interactions that appear in Feynman diagrams, and we typically represent them in Feynman diagrams by a new interaction vertex that's labeled by an x. Okay. So here I've written down the very simplest interaction vertex, just describing y phi, which is just a single x for the interaction y with one leg, one particle leg coming off of it. And it's defined so that it cancels all of the contributions to the one-point function coming from all of the other diagrams in the theory. So in practice, of course, we never need to actually compute the value of the coupling constant y. Okay. So we don't actually need to compute y. We just need to remember that it will cancel any diagram that has only one leg. That is to say, any tadpole. So this actually has a very interesting consequence, which is something that we actually mentioned last semester, but I'll remind you of again. So it means that not only do the one-point functions all vanish, because we've adjusted the value of this parameter y to make it so, but it means that in any Feynman diagram, expansion of a scattering amplitude we can ignore any diagram which has the property that if you cut it in two, or that is to say, if you cut one line, then it will form two pieces one of which is not connected to any external vertex. So let's just see that a little bit more explicitly. So for example, we saw that the coefficient y is defined such that this counter term at leading order in the coupling constant g will cancel the one loop contribution, so at order g. So that means, for example, that if we were considering 2-to-2 scattering, then you might naively think that you would have, say, a one-loop correction that looked like this, but you would also have a counter term involving the new coupling y that looks like this, and then these two terms would cancel against each other. And so you can see that you can just effectively ignore any of these Feynman diagrams that you get just by attaching on an extra tadpole, or taking one leg and attaching on some other piece of the Feynman diagram. Is this clear, more or less? We actually discussed this last semester, but I wanted to return to it just to remind you of it, because it's another very simple example of how we use counter terms in order to enforce physical conditions in the Feynman diagram expansion. And in this case, it's a very easy physical condition to enforce. It's just the condition that there are no tadpoles. Okay, so this is sometimes called as the no tadpole result, or the no tadpole theorem. Any questions on this? Okay. So we saw that enforcing the physical condition that the one-point function vanishes as a condition on the coupling constant y is very easy. But for the other counter terms, we actually have to do a calculation. And so starting next class, what we're going to do is we're going to develop some of the technology to compute some of these loop diagrams, and we're going to start computing some of these other counter terms in phi cubed theory to start explicitly. Okay, so we'll start by enforcing the condition that all of the physical excitations have mass m, and that the one particle states are normalized appropriately, and see explicitly what that means, how we enforce those conditions on these counter terms. And in practice, often we don't end up actually computing the values of z order by order in perturbation theory, but instead, just as we did in the case of the tadpole diagrams, just noting that by enforcing these, we enforce some sort of physical condition that we can then just impose directly on our results. And as we'll see, this will automatically remove many of the divergences, well, all of the divergences that will appear in quantum field theory. So starting next time, we'll calculate what's called the self-energy of the particle, or the, really the self-energy of the scalar field, before moving on to study the self-energy of photons and electrons in quantum electrodynamics. Any questions? So maybe I should stop here. I guess, well, okay, I've run out of time. So maybe I should just stop and see if there are any questions. Any questions? This is more or less clear. So this class was a bit of a review, but next class we'll start into some new stuff.
So,
Yes.
So in the Lagrangian that you wrote, with all these added constants, and why is it the only dimension full constant that you added? That's just because.
Yeah. Well, G now in phi cubed theory, G is a dimensional constant as well. So we'll get back to how to deal with dimensional full constants. In fact,
The z's are all
Z.
dimensions, though, right? And then the y.
The Z's are dimensionless. Yeah, we'll get back to that. Yeah, I mean the dimensional. Okay, we're going to spend a lot of time doing dimensional analysis. In fact, yeah, normalization is basically Well, there's a lot. It's basically dimensional analysis, but there's a little bit more. There's a few integrals one has to do as well, but it's mostly dimensional analysis. With a strong knowledge of dimensional analysis, you can do just about anything. Good. Any other questions? Good. I will see you on Thursday.